my name is Diana Cheng, and I'm a Senior Solutions Architect at AWS. I'm working with financial services customers, and I'm here today with my colleague, Alexander Günsche. He will deliver the talk with me today. In case you don't hear me and I need to speak up a little bit more, please let me know. So we've brought to you this talk today. We'll start today by discussing some well-known integration patterns for microservices and distributed systems, patterns that helps us architect with scalability, possibility to evolve our systems, and some reliability in that communication. And then we're going to talk a little bit about some characteristics of SaaS applications, of what we've seen SaaS applications have as common denominators that makes them successful. And then we're going to present to you some new patterns that we've brought in today that build on top of the existing traditional patterns for application integration. And yeah, hopefully this will be interesting for you. And to set the scene a little bit, I'd like to talk about what's the motivation for this talk, or why are we here today discussing this in the first place. So I think patterns are very useful for everyone who's a developer, an architect, and technologist in general, because they become a common language, kind of a lingua franca, in which I don't have to explain every detail of the context that I'm talking about. As long as I can mention a well-known pattern, then everybody understands already what I'm referring to. And this helps us communicate with each other. In the context of SaaS, we'd like to see what we can build for the different stages of a SaaS application, or the different stages of the life cycle of a SaaS application that builds on these patterns that we can benefit and establish as best practices to work with. So let's start by reviewing some of the traditional or application patterns that we can use in our ecosystem of microservices, or basically in any type of distributed system. And the first one is the traditional synchronous request-response pattern. What we have here is a direct integration between two parties that know about each other, and it's based on HTTP. This could be also a REST API, and it's pretty low latency because basically the request is processed immediately as soon as it's triggered and makes the round trip to the other side. It's pretty simple because as long as you understand the semantics of HTTP, you understand what's going on. There is not much else to it. And it's fail fast because either you will receive a response that will contain an error message in case it fails, hopefully with proper semantics and error code and an appropriate error message, or the request will simply time out and you won't receive a response. Some of the other characteristics which might present some challenges for us with this type of integration is that the receiver might fail, right? And it's the sender that needs to cope with those failures. It needs to take care of attempting a retry and basically work with that failure. Also, there might be some requests that come to the receiver that get throttled. If the receiver is receiving peaks and is not able to cope with the load that's coming to him, then it needs to throttle some requests and return a response to the sender. And the sender also needs to understand why and what can be done about it and how to retry that. If we think about this pattern and we think that we might be integrating multiple microservices in the landscape of our application, and we think about calls that go downstream to other services, we might imagine how we are blocking resources in every step of the way, because every call is waiting for the next one to complete. And we block some resources and while that happens. And if there are some errors in the downstream service, this can actually compromise the entire chain of requests. And the problem becomes even more complicated when upstream services attempt to retry, and they can't really deplete downstream services or applications from resources completely. And this is why we have some mitigation patterns, or some patterns for mitigating these problems, such as circuit breaker. But this is not the only pattern that we have, and I would like to switch to a different mode of thinking about how we can integrate our applications by presenting this quote. This is from our VP and CTO of Amazon, Werner Vogels. He said in the last edition of reInvent that the world is asynchronous, and there are trillion of events. It's event-driven, and there are trillions of events that are taking place around the world. And in spite of that, the world keeps working, right? It keeps moving. And so should our applications. So regardless of what events are coming into the different parts of our system, things should keep on working. If some part of the application or some microservice in our landscape is not working, things should still be working in the rest of our system. And no matter what new functionality we might be wanting to introduce into our application, things should still keep on working. And that makes a lot of sense to me. And I have a second quote that I brought, that this is also from a former colleague of ours, who said that if your application is cloud native, it's large scale, and it's also distributed in nature, but doesn't have a messaging component, that's probably a bug. I also think this is right, not only because of the downsides or the disadvantages that we saw with synchronous integration, but also because some things just simply take too long to wait for them, and other times they are just asynchronous in nature. And this is where messaging brings that asynchronicity, that way of integrating applications in an asynchronous manner. So we have some patterns here as well, and we can categorize the patterns based on the type of messaging channel that they use. The first type of messaging channel is a point-to-point channel, and it's basically implemented as a queue. A queue is a messaging component that will decouple the sender and the receiver that we see in this diagram. These two parties no longer have to know about each other, and the sender simply takes care of knowing where to send the messages, in this case, this messaging queue, and the receiving will simply consume them from them. In principle, this is a one-to-one communication, or just one-way communication, let's say. But that doesn't have to be the case. We can also implement a request-response pattern in a synchronous manner if we provide a response channel to receive responses from the receiver or consumer of the messages. For this, the sender needs to specify a return address or a channel, the address of the channel, where the receiver should put those messages. And this is pretty good to have when the sender actually needs to know what happens with the messages, if he needs to understand that the message has completed being processed, or if it needs to actually have the result of that processing himself. What the previous picture didn't show is that, in fact, we can have more than one receiver. We can actually also have more than one sender. And because of the semantics of how queue work as a messaging system, each message will be processed by just one receiver. So every message that gets picked up to a queue gets delivered only to one consumer and not to any other. This creates the effect that we can scale on the right side of our diagram. We can add more receivers, and this will speed up the rate at which we can consume from the queue. The more receivers we add, the more they can pick up messages from the queue, and that way we control the rate at which the messages get processed. If we don't want to scale more on the right-hand side of the diagram, we don't have to do that. We can simply rely on the queue to be a buffering mechanism that stays in the middle and creates and protects the receiver or consumers from peaks or increased load in traffic. Some of the services or the service on AWS that implements a queue is Amazon SQS, or Amazon Simple Queue Service. And to summarize a little bit the characteristics that we see here, we have a temporal decoupling now from the server and the receiver, because the sender sends the message but is not expecting a reply. The receiver will consume them at the rate that he sees fit and at the rate he can cope with the message load. And it will have nothing to do with the time, necessarily with the time at which the sender sends the message. Using a queue also makes the receiver more resilient to failures, because the semantics of consumption from a message queue is that if the receiver is not able to process a message successfully, then the message goes back into a queue and it can be picked up by another consumer or receiver to be reprocessed or retried. So there is some retrying mechanism kind of inherent to the message channel, which we didn't have when we had synchronous HTTP-based request response. As we mentioned, we control the rate of consumption from the queue by scaling on the receiver side. Of course, one thing that can become a little bit complicated is now the sender is completely decoupled from the processing. So if he needs a response or he needs a reply, then he needs to keep on checking on the response message channel where that is, and it's not like he's gonna rely on automatically receiving that response. The other asynchronous message pattern that we have is based on, it's called publish subscribe, and is based on a topic as a messaging channel. Now the sender is called a publisher, and the receivers are called subscribers. The publisher sends messages into the topic, and every single message that comes into the topic automatically gets pushed to all subscribers. This pattern is a little bit similar to how we listen to messages on a radio. It's kind of a broadcast to all subscribers. When we're listening to the radio, then we get the information, but for as long as we're actually actively listening. But if we switch off the radio, or we, for example, take one subscriber offline for maintenance or for upgrades, then the subscriber is no longer receiving that information. Those messages will not get to him. And the different implementations of topics, the different products in the market implement retries from a topic, so pushing from a topic in different manners. But that's kind of the principle, that as long as the subscriber is online, he will receive the messages. If not, he will miss them. And as soon as he comes back online, then he will start receiving the new messages that come into the topic. What we also see here is that because of every message receives, every subscriber is receiving every message, then we don't really have a way to scale on the subscriber side. So if we want to process more messages more quickly, then adding more subscribers on the right-hand side doesn't do anything, because there will still be all the messages delivered to that subscriber that you added. So it doesn't really help us scale. And that is because the topic doesn't conceptually provide any buffering, like the queue did. So how can we scale on the consumer side, right? So how can we scale the subscriber side here? And the answer is actually the topic queue chaining pattern, which is a more advanced pattern, which we don't have time to cover today, but which is covered in a talk that was previously presented at JCon in the last 2 years. It's an integration and conversation patterns for microservices by our colleague Dirk Fruner. So you can go into that URL, access the YouTube video, and you can learn about these patterns. There are other ones, like, for example, scatter gather, and more that we don't have time to cover today. But that was just to provide a foundation or some understanding of the basic integration patterns that we have for distributed systems. And with that, we make now a excursus into SaaS. I think you might all be familiar to some extent with SaaS. How many of you are working in building a SaaS application currently, or have been in the past involved in building SaaS solutions? Okay, that's pretty much half of the audience, so it's pretty good. And I'm not going to cover what SaaS is or what are the characteristics of SaaS solutions. What I try to do today here is to recap some of the characteristics that make SaaS solutions successful and that we've seen in the wild and working with our customers. And there are many different ways to build SaaS solutions, and there is no one blueprint or one architectural reference that you can take out and say, hey, now your architecture is supporting SaaS, or now you've turned your business into SaaS. There are many different ways to build a solution, but what we consider to make to be part of a successful SaaS implementation is not just the application level multi-tenancy that you have in this box, in this gray box in the middle. It's also all the components around it, that control plane that allows you to have this cross-cutting concerns or cross-cutting functionality centralized for your different tenants. Your onboarding, how you're onboarding new tenants into your application, how you're onboarding new customers and providing them with an identity, how you identified your tenants from one another, Are you working with different identity providers to identify your users? Are you going to have a different identity provider per tenant, for example? How do you do provisioning? Do you do it at during tenant creation, or do you do it before? What is that automated deployment pipeline that you have that deploys your application across tenants, or that's a single deployment across tenants? What is that single pane of glass where your metrics are, where you can also monitor usage and do proper metering so that you can bill your customers, and how you decide to do that billing on a per tenant basis, per usage, perhaps per feature, per user. That all of that management, all of those cross-cutting, centralized cross-cutting concerns allow you to have more scale, to build at the scale your solution, and to be more efficient and have agility when onboarding new customers. So that's what we see. And in terms of resource usage or consumption resource consumption model for your application level plane, we also see some models. The first one is silo. I think it's pretty self-explanatory. You have dedicated resources per tenant, which there is simply nothing shared. In this case, in the diagram, you see the entire stack being isolated and non-shared across tenants, and that's one way to do it. On the other end of the spectrum, you will have what we call pool, where resources are shared across tenants, and you might share everything, but we also have a mix of both, which is what we call bridge. We don't typically use the term bridge very much. This is simply the fact that some resources will be consumed or provisioned in a silo way, and some others will be used in a pool model, and you will be sharing those resources across multiple tenants. And with these models, there are some pros and cons, some advantages or disadvantages. Of course, it's much easier when you have isolated resources or even isolated stacks to achieve the compliance, the data isolation, and the data privacy concerns that your customers might have. You also don't have any sort of impact from other tenants, such as noisy neighbors. If you have a lot of activity on a given tenant, that you don't have to worry that might create some sort of service degradation for other tenants. And most importantly, the availability of your tenant is not compromised if some resource is down. So as resources are isolated, if a given resource gets compromised or is unavailable, then that doesn't have any impact on the other tenants. But of course, the pool model also has some advantages that you will not gain with the silo model. So you have more direct and centralized management and rolled out of your application. You can leverage cost synergies a lot better and reduce cost by sharing resources. But of course, you will introduce, you will need to take care on an application level on mitigating cross-tenant impacts, such as noisy neighbor, and also separating cost to do proper billing and metering for each tenant and for every user becomes a little bit more complicated. At the end of the day, there is no one way or the other. Whatever architecture or mix of these approaches you choose, at the end, important thing is that it supports your business goals, that you are able to provide frictionless onboarding for every new tenant that you onboard and for all the users of that tenant, that you really have this control plane that allows you to do zero-time downtime deployments, that you have single pane of glass where you have monitoring for all the tenants that you work with, and that you have that centralized usage view and consumption view for the different tenants. As long as these goals are supported, then you can mix and match the different resource consumption models that we've mentioned. But after having given now that introduction to integration patterns and to SaaS, I'm happy to hand over to Alexander. So he can talk about the SaaS integration patterns that we brought today.
Yes, thank you very much, Diana, for a great recap of general communication patterns in asynchronous architectures and for setting a scene with what SaaS architecture means and what common patterns we see there. So I didn't really see who has been working on SaaS, but I think we all understand these are multi-tenant applications, usually for e-commerce businesses and things like that, but it can also be a wide range of applications. Now, what we are now looking into is discussing patterns that we have seen with our customers when it comes to integrating in event-driven ways with external systems. So that might be a central SaaS platform like in e-commerce with multi-tenant stores, but it could be that there is another SaaS application that needs to contact it and maybe set up a new account or send messages into it or wait for a back channel information. And these are the patterns we would like to discuss today. And they are just examples for other patterns that we see. Some of the things we see maybe aren't fit to be called patterns yet because, as Diana said, these are usually established ways to do it, kind of no-brainers to architecture, but we will collect them. So the three ones you see today are just a selection of successful patterns that we see. And these three are first, in a design phase, you would think about how to isolate channels across different tenants. When you onboard new users, and this is a crucial part of a successful SaaS application, how do you make it frictionless as possible? And this is a pattern we call sign up before subscribe that we will discuss today. And the third pattern would be webhooks that you will be using at runtime. So let's have a look at the first pattern here. Click, click. Nope. Oh, there we were. Sorry, takes a bit of time. All right, so the first pattern we discussed today is called channel isolation. And just a few minutes back, we have heard about tenant isolation, and indeed this is related. We are using slightly different terminology here, and you will see in a minute why that is, but we will also think about how to allocate resources to different channels for incoming messages. And if you remember, we have seen two basic patterns of tenant isolation. So we have seen previously the pool model, the bridge model, the silo model, and as a kind of a mix between them, the bridge model. But here we speak of a shared channel because in this case you basically have a set of infrastructure deployed for all of your tenants at the same time, and they would share that resource. As a second model, we have the exact opposite of that. It would be a dedicated channel model. And in this case, you would deploy infrastructure for each of your tenants individually, and they would have that allocated for themselves. And the third approach that we've seen and we think is applicable is a sharded approach. So not shared, but sharded. If you are familiar with messaging systems, you might know that a shard is a group of channels that you have. In this case, we would allocate a group of tenants to a shard of message stream. And this could have several advantages in terms of performance, security, and utilization of your infrastructure. Now let's have a look at a shared model, how that looks like in practice. And it's quite simple, right? So as you see, we are using AWS services here, but if you're not familiar with AWS, this translates well to other infrastructure services, more generic ones, or from your favorite cloud vendor. The point here is that we have a queue, as described previously by Diana, which is a service that would hold messages until they are being pulled from a consumer. In this case, we are using AWS Lambda, but it could as well be a virtual machine or a container of your liking. The point is all of your tenants share this infrastructure with all pros and cons that this has. And if you feel that in your setup you would more benefit from dedicated channels, you would set up a model that would more look like this one. So the basic building blocks are the same. You still see that we are using queues. We still are using, in this case, Lambda as a function as a service to pull messages from. But now each of your tenants has their own dedicated infrastructure. And we will later discuss the advantages of that. But you will see one of the implications on the on the right-hand side from your perspective, that you will have to deploy infrastructure individually per tenant. So as part of the onboarding, as part of the setup of your tenant environment, you will have to set this up. The advantage of this is that you have a much higher degree of security, because it might be that a hijacker would take control over some functional parts in your application, but if they do that for one tenant, it's still isolated on the infrastructure level. Another advantage would be that you can allocate the resources per tenant, and depending on, I think Diana has introduced the term noisy neighbor. So if you would have a tenant that consumes a lot of resources and would put other of your tenants at risk of exhausting resources, then this would contain them into their resource allocation. And the third model that we have seen is, as mentioned, the sharded channel model. This is a mix of both worlds, and to be honest, it is even a bit more complex than the dedicated allocation, because now you don't only have to set this up per tenant, but you have to keep track of which tenants are allocated to which of your shards. But from there are some advantages to that, and that is that you still have a fair isolation between tenants, so the blast radius is a bit lower. And the good thing is that you can map this to your billing tiers. So you could say, I have a billing plan that is more for free users or for simple users, whatever you call them in your business model, and you would have, let's say, 100 users per shard. But then you have those pro or premium or enterprise users, and they would then have just 5 of tenants, or even just a single tenant. So you could basically also use this for a dedicated allocation. Okay? So if you look at this side by side, you will see in a shared channel we have the advantage of an optimum utilization of your infrastructure, whereas you would still have the danger of noisy neighbor. With dedicated channel, you will very much benefit from security and allocated resources for that particular channel, but it's more complex to set up. And finally, in the sharded model, you will see that you can take a tiered or balanced approach to it, so you still have the possibility to move customers around. You still can benefit from some cost optimizations across different shards, but you still, of course, have the increased complexity and danger that somebody would exploit the channel and kind of get access to messages from other of the tenants. So the second pattern we would like to discuss today is called sign up before subscribe. And again, I'd like to kind of picture this in an environment where you are the provider of a SaaS application, but the world in which we live is not just one application to rule them all, but we think in ecosystems, right? So you will start your business around your own SaaS application, but I guarantee you 3 weeks later, you will have the first potential partner who wants to integrate their solution with yours. And it's beautiful, it's great. So customers have a lot of choice, and we have an ecosystem of things working together. And this pattern in particular is for a scenario where an external platform would set up a new tenant in your platform. Okay, so this means we talk about machine communication, and you might think that this would be very well suited for a, let's say, atomic process, right? There's a lot of things happening when you sign up a new user. You will have to get their information. They will have to subscribe to a billing model of your choice. And as discussed, you might be in a tenant isolation model where you have to provision infrastructure for them. Now, it might make sense to say, well, we consider this to be some sort of transaction. So in database lingo, and he would say, if one of those things fails, everything fails, I will roll it back, but if it's successful, only then the account will be usable. That makes sense, that makes a lot of sense, and certainly that's a good way to start. However, what we feel is that from a usability perspective, and in the end, machines are also users in that sense, it makes more sense to split that process into 2 parts, where you would say, the first part, that is a bit simpler. You sign up the new tenant and give them a response. And as soon as they are signed up with their basic information, you could say, your account is usable. Doesn't mean a lot because many of the moving parts are still not there. But in the end, customer gets the feedback, the other platform gets the feedback, and then they can take this and go on with the actual heavy lifting. And that is the setting of the billing, resource provisioning. You might have to contact an external payment service for the credit card, things that are happening in the background, and that all can be deferred. And yet the customer and the external system can already interact with your system. So let's have a look how this works in practice. Again, we are using AWS technology, but again, this is, would work with other solutions as well. So bear with us, hopefully. The point is we have a simple HTTP endpoint called signup in this case. And it would require very little information to kind of work. It would require the tenant's name or maybe an email address, but that's about it. And from what happens in your application then is you would take that through some sort of API gateway. We are using step functions here as an orchestrator, but in terms of what actually happens in the application, the first thing is you would just store it in a database. We're using Dynamo, right, AWS, but basically persisting the information you just received. And the second thing you might want to do is put this into your identity management system, which is in our case Amazon Cognito. That's it. And after that, you can give back an information to the calling system, either as a token of some sort or a email verification link if you want to kind of propagate this to the actual customer. And now the account exists. And if something fails, you can reach out to them and see what needs to be fixed. You can analyze it and so on. Now for the heavy lifting, we have a second endpoint, which would be called subscriptions. And with the token you just returned to the caller, they can now initiate the actual setup of this tenant and their environment. So the first thing that would happen is, again, we will complete the identity information in our management system, Cognito, and, for example, create a password of some sort and allow that account to be used for login. In the second step, we would then complete the tenant data with billing information and other metadata about their environment in our database. And then as a third step, optionally, depending on your infrastructure model and your tenant isolation approach, you can then do the actual heavy lifting of creating all the resources that are necessary to actually operate that environment for the tenant. And when all this is done, you have completed the onboarding process for a tenant and can then, through another channel, inform them that, look, here's your credentials, your shop or whatever is now fully usable. And then they are able to use the application itself, right? So this is all happening in the control plane, in the part of your application that deals with the relationship between yourself and your customer. And then they can offer that application to their own end customers, right? And this is how you complete this integration in a decoupled way, where you allow things to fail and recover and investigate them without rolling everything back and having kind of dead entries in your database. Okay. Now, again, this is a pattern we've seen being successful. You could think of other extensions to this, right? So you could think to say, why do we need another subscriptions endpoint? I could just inform the other system of something that has happened in my environment later on through some back channel. And this is, in fact, a third pattern that we'd like to discuss today, and it's called webhooks. And webhooks are nothing new. They are a very common approach, an architectural pattern that we've seen in web applications for a long time. And what's special about webhooks is that they are kind of a reverse API, right? So you could say there are HTTP callbacks, because opposed to a traditional web service API, they are used for notifying other systems. And the nature of a webhook is that basically the client, the system that makes the request, imposes the semantics of the interface to the server. So this may sound a bit abstract, but if you imagine, for instance, GitHub, when something changes in your repository, some lifecycle event like a push being made to your repository, then GitHub can trigger external tools with webhooks. And that's what they do, right? So if you have some CI/CD tool working, making a package or running a test on your behalf, then this is exactly what GitHub does. They have integrations with other providers. They define the interfaces more or less, and they say, I can ping you when this has happened in my system through that event HTTP mechanism, okay? So this can be useful for that kind of application, but you can also use it as a response channel for a REST API that you're offering yourself. So imagine you have a service that would create some sort of entity, but instead of returning the entity right away, it would give you an HTTP 202 code, which means I've accepted your request. I will not act upon it right now, but maybe in 5 minutes or a day or whatever. And of course, you as the client want to be informed when this has happened. So what you can offer as the service provider, say, look, I will not give you something right away, but I can notify you when it's happened. So please open some sort of HTTP server for me to inform you with that kind of payload, and you will know when it's done, and you can then continue working with that new entity. So from an implementation perspective, it would be, look a bit like this. We are using an event router called Event Bridge in this scenario, but in the end, it's just a broader messaging channel that you can use across your application. And as you see above, we have a payload, in this case, something business specific based on a card, but you also see that we have a tenant ID in here. Ideally, so if it's machine-to-machine communication, we will also have some sort of token that authorizes us, right? But we leave that out for now. But you may imagine that we have secured this. So as soon as the message comes into your event router, this would trigger some sort of activity in your infrastructure. So in this case, again, we are using step functions for orchestration, but the actual logic happens here. Based on the ID that is in the payload, we can now identify the tenant and say, okay, in our large database, we have found that this belongs to tenant number 1. And as soon as we have identified them, we can now do the actual processing, say, okay, based on the payload and the business logic involved with that, we can now call the actual system that will process this, in this case, an HTTP endpoint. So imagine you would have a microservice that deals with that particular work. And the interesting thing is, this entire event mechanism around the event router and the step functions and those things happening in there is completely decoupled from your actual SaaS core application, right? So you might have something in this case that is more shared across tenants, but in the tenants themselves could be living in a silo, pool, or bridge model. That doesn't matter because we have identified the tenant by their ID in our mapping database. And now you say, okay, we have now an event flow, something comes in, something's being propagated, but how does the caller know what has happened? And the good thing about this mechanism is we can play it in both directions. So we can say we have posted it to our HTTP endpoint that is in our own kind of domain. But we can also play this backwards and say, okay, now we give a response, or we get a response from this service, in this case, something about a discount, and we play this completely back to the other system. So we play kind of event ping pong here, right? So it's not a technical term, right? So please don't note that down. But the idea is that you have event-driven communication in both ways. So it's not, something that is vendor-specific in terms of your infrastructure. So these are just examples of how you would implement this. The point is that you can use kind of HTTP and vendor-neutral mechanisms here as well, but you would set up the interaction between an external system and your system fully event-driven, right? And coming back to the quote that Diana said earlier from Werner Vogels, that's the whole point, right? So we think a lot in those synchronous REST APIs, but if you try to decouple, if you try to get load off, if you want to defer things that don't need to happen in real time, use these mechanisms in order to communicate in an event-driven way. Use buffers and queues in order to put messages there. We see this a lot in logistics where, for instance, you don't need to get the email that your Amazon package has been delivered right away. It can take 5 minutes, right? And this will take a lot of the strain on your actual architecture, right? Okay, so these are the 3 patterns we have brought to you today. What are the takeaways from this whole talk? As Diana already said, there are no common blueprints for SaaS, right? So we are working with, I don't say a number now, a lot of SaaS vendors. Again, many of them have their own approach. It's a business problem in many cases. It's a two-folded business problem because we are talking about the relationship between the SaaS company and their customers. On the second layer, the customer with their own end customers. So there's always a lot of business requirements involved there, right? But as you know, as developers, as architects, patterns can help you. Patterns are no-brainers that can solve generic problems for you. So if you can think of some that maybe you have seen in the wild, reach out to us. We're always happy to kind of extend on them, maybe improve the ones we already have. And finally, as always, use your common sense, choose the patterns that fit your requirements in order to not just do it for the sake of having applied a pattern, right? Okay, so Yes. Okay. So where do we go from here? We have collected some resources for those in the very back. I'm not sure if you can scan those codes individually. Please take a photo and see if you can scan them afterwards. Otherwise, reach out to us and we will be happy to send you the links. This is about further resources that we have around SaaS. Again, we're doing a lot of this. We've seen a lot of successful patterns. So if you happen to know what the well-architected framework is, this is a collection of best practices, and we have extended this with a so-called SaaS lens, where we discuss successful kind of approaches and practices around SaaS. But we also have a lot of resources and tooling and documentation around SaaS in general in the AWS Factory, and a large body of resources in the general SaaS area on AWS. So feel free to dive in. Reach out to us. We're always happy to hear what people are doing in the wild, regardless of your infrastructure provider. So let us know what you're doing. As a final, before we go to Q&A, I'm not sure if we have time for that. As a final point, I'd like you to give us a bit feedback how you liked it today. We are very data-driven, and so hearing from you how you liked it, what we could improve, and what we could extend on would be very welcome. So please check the link or the QR code and let us know what you think. And I think it gives us a few minutes for Q&A. Do we have that? Yeah, I think so. All right. Any questions? None. Is that a good sign or a bad one? I don't know. I hope you're happy. You have taken away what you needed. Again, let us know if you are interested in those things. And
you prefer to come down here and talk to us one-on-one and ask some questions, or we can exchange also.
Absolutely. Thank you, Diana. So we'd like to thank you very much for today, for being with us today. Have a good day.
Thank you.
Thank you.